So in this lecture, I have done from question number 35 to question number 38. Okay, irrespective of you are preparing for advance or not, okay, it's very important that you see these lectures or you follow through the questions. Okay, important aspect of relation between potential and electric field is given. Okay, the importance of graphs are given, or how potential energy and electric fields are related, how the graphs are drawn. So treat this as one of the important lectures from JEE perspective. Okay, even for means, it doesn't have to be advanced. Okay, see, in this question, the potential is given by A dot R. Okay, we have to find out the electric field in the space. Now, the first question that I have is, what is the relation between electric field and potential? Okay, see, what do I know about work done and force? We know that work done is equals to force dot displacement, isn't it? Or dot product of force and displacement. Okay. Now, if I say the forces that are acting on the body are all of conservative nature. Okay. So can I write minus change in potential energy is equals to force dot dr? Why? Because potential energy or difference in potential energy is nothing but work done against a conservative force or negative of work done by a conservative force, isn't it? Change in potential energy is nothing but negative of work done by a conservative force. See, if you took a block from out here to out here, okay, change in potential energy is nothing but mgh. Okay, final potential mgh, initial potential 0. Work done by gravity is nothing but minus mgh. So similarly, work done against a conservative force or work done or negative of work done by a conservative force is nothing but change in potential energy. Okay, so minus du, if all the forces are conservative in nature, I can say that work done is nothing but negative of potential energy difference. Fair and fine. Now, what is potential energy of 1 coulomb or plus 1 coulomb? Potential energy of plus 1 coulomb is nothing but potential. So I can write this as minus dV. What is force on 1 coulomb? Force on 1 coulomb is nothing but electric field dot dr. So this formula can also be written as F dot dr, or dV is nothing but E dot dr. Fair and fine. So I got the relation between potential difference and electric field, where minus dV is equals to E dot dr. Now the problem becomes very simple. Potential energy is given by A dot R. Okay, so I have to find out electric field. So from this equation, I do know that electric field is equals to minus dV by dr, isn't it? Fair and fine. So out here, electric field would be nothing but minus dV. What is the value of V? I have written this a little bit wrong. Minus T into what is the value of V? AR by dr. So electric field is nothing but A will come outside and dr by dr becomes 1. So negative of A. Okay. So this was our entire question. Now I do have to discuss some aspect of the previous question. The thing that I'm going to discuss is, we do know that minus dV is equals to E dot dr. Okay. Or electric field is equals to minus dV by dr. Fair and fine. Out here you have to notice two things. The first thing you have to notice is potential. Okay, this is a scalar quantity, whereas electric field is a vector quantity. Okay, so if equation of potential are given, potential will be given by equation something like ax square plus by square plus cz cube or z square, or a minus b whole square, or anything. Okay, cz cube. Okay, it doesn't matter what the equation is given. Understood? For example, this is example. The equation of potential is not necessarily this value. This is just an example. Okay. Now suppose the equation of potential are given. Okay. How do I find out the electric field from the equation of potential? See, we know that electric field is equal to dV by dr. Fair and fine. But out here, how do you differentiate R? Out here x square is there, y square is there, z square is there. How do we differentiate this thing? See, r vector or displacement vector can also be written as xi plus yj plus zk, isn't it? So electric field at any point in space can be written as a combination of electric field in x direction vector plus electric field in y direction vector plus electric field in z direction vector, isn't it? And what is electric field in x direction? Electric field in x direction is nothing but minus d into v by dx. Electric field in y direction is nothing but minus dv by dy. Electric field in z direction is nothing but minus dv by dz. Okay. Now for example, if I have the equation of potential this value, okay, just for example, the equation of potential might be anything that would be given in the question. But just now for example, if the equation of potential is given by this value, how do I find out Ex, Ey and Ez? See out here. Ex would be nothing but minus d ax square plus by square plus cz cube divided by dx. Okay. Now while differentiating this entire term with respect to x, okay, any other variable other than x would be treated as constant. Okay, and this type of differentiation is known as partial differentiation. Understood? So while I'm differentiating with respect to x, y, b, a, c, z cube are treated as constant. So our answer would be ex is nothing but minus 2ax. Or differentiation of ax square is nothing but 2ax, minus came from out here. By square is entirely constant, cz cube is entirely constant. Any other variable other than x is treated as constant. Similarly, while differentiating y, okay, ax square plus by square plus cz cube, that is the equation of potential, divided by dy, which is nothing but any other variable other than y would be treated as constant. Okay, so this differentiation would come as minus 2 by. Okay, I made a mistake of differentiation out here. Minus 2x. Okay, not 2ax square, 2ax. Okay, similarly for z, ax square plus by square plus cz cube divided by dz. Okay, minus 3cz square. I'm differentiating only this term with respect to z because all other terms other than z are treated as constant. Okay, so electric field in x direction is given by minus 2ai. This is I cap because this is the x component of electric field. Okay, similarly y component of electric field is given by minus 2 by j cap, and z component of electric field is given by minus 3z square k cap. So x is nothing but minus 2a x I cap, ey is nothing but minus 2 by j cap, and ez is nothing but minus 3cz square k cap, isn't it? So electric field is nothing but minus 2axi minus 2byj minus 3cz square. This much is understood. So all I have told you is, if an equation of potential is given, how do you derive the electric field? You derive the electric field by using this formula or this method. You differentiate the entire potential with respect to x first, make it electric field in x component, y second, electric field in y component, z, electric field in z component, and apply minus. Don't forget about this minus. Okay, understood? Now suppose equation of electric field is given in the question. Okay, in the first part the potential was given, find out the electric field. In the second part of the question, equation of electric field is given. Okay, you have to find out the potential or equation of potential. So you have to apply the same formula. Okay, minus dv is equals to E dot dr. That means you have to integrate it. Now how do I integrate this type of equation? See, you can already look back and say the potential of this thing would be this one. Okay, but you know that you have to do integration. But suppose only the electric field was given, okay, you don't know anything about this one, you don't know anything about potential. How do I derive potential from the electric field? Okay, see, we know that minus dv is equals to E dot dr. Problem is r is nothing but x, y, and z. How do we integrate I component, j component, and k component with dr? See, the x component of electric field has to be integrated by dx. That means what I'm trying to say is minus dv is equals to, what is the x component of electric field? Ex dx integral plus ey dy integral plus Ez dz integral. This much is understood. See, our basic formula was minus dv is equals to E dot dr. Okay. The problem I have is r is a vector quantity which has I cap, j cap, and k cap. Electric field is a vector quantity I cap, j cap, and k cap. Whereas potential is a scalar quantity. You would have only a equation, no caps. Okay. So if potential is given, you find the electric field by using this method. If electric field is given, you find out the potential by using this method. Or minus dv is equals to, what is the value of ex? The value of ex is nothing but x component of electric field, or minus 2ax dot dx, okay, plus y component of electric field is nothing but minus 2by into dy, plus z component of electric field is nothing but minus 3cz square dot dz. And if you integrate this one, no, would get minus dv or minus v, okay, minus v is equals to how much? Minus 2ax square by 2, or it would be nothing but same as this equation, ax square minus ax square minus by square minus cz cube. If you integrate this one, you will get this value. Now if I multiply minus, v is equals to ax square plus by square plus cz cube. Now some of you might have doubts, sir, what happens if potential has I cap, j cap, and k cap? Potential will never have I cap, j cap, and k cap. Potential is a scalar quantity. Okay, understood? So this equation will never have I cap and I cap, j cap, or k cap. This equation can have values of x, y, and z. That I agree. Okay, a point in space can be defined. Potential can be ax square by, or ax by b, or ax by y into z, anything. X, y, and z can exist, but I cap, j cap, and k cap cannot exist out here. Out here, I cap, j cap, and k cap will compulsorily exist, irrespective of x, y, and z. It can be, see, out here electric field can be given as minus tay I. Y doesn't necessarily represent that x component of electric field. The I cap represents the x component of electric field, j cap represents the y component of electric field, and k cap represents the z component of electric field. So this is the main thing you need to remember out here. Do not go, or do not confuse between x, y, and z. Follow the I cap, j cap, and k cap. Understood? Potential will never have I cap, j cap, k cap. Okay. Electric field will always have I cap, j cap, k cap. Okay. And x, y, and z variables of x, y, and z can exist in both the equation of potential and electric field. So x, y, and z are irrelevant out here. We just have to differentiate with respect to them. Follow the I cap, j cap, and k cap. Now this part of the question becomes simple. Two equations of potential are given. We have to find out the electric field of this one and electric field of this one. So part A. Electric field is nothing but Ex plus Ey plus Ez, or minus d of a x square minus ay square. See, I'm just combining these two, a with x square and a with y square. I just multiplied inside. Okay, divided by dx I minus dx square minus ay square by dy j cap minus dx square minus ay square by dz k cap. So electric field out here would be nothing but minus 2ax and y is treated as constant I cap minus, okay, minus 2ay j cap, and since there is no component of z in this equation, this entire term would become 0. So electric field is nothing but minus 2ax I cap plus 2ay j cap. Similarly, part B of the question, potential is given by axy. So electric field, okay, uh, electric field is nothing but minus dAxy by dx I cap plus, sorry, plus into minus is nothing but minus only, no? So dAxy by dy j cap minus dAxy by dz k cap. If I differentiate this term, treating x only as variable, everything other as constant, so out here E would come as, but electric field would be nothing but minus ay I cap m, but y out here is constant, a and y out here is constant, a and x out here is constant, a, x and y out here is constant, okay. So minus ax j cap minus 0, because there is no component of z out here. And see, this was the thing I was talking about. This out here is the electric field in x component out here. This out here is the electric field in x component, although this has a term of y, because this is nothing but I cap. I cap means electric field in x component. J cap means electric field in y component. Okay, so this is the electric field in y component. This is the electric field in x component. The variables are just nothing but point in space, okay, or the coordinates in space, okay. Now the second part of the question is asking, draw the graph of these electric fields, okay. So before drawing the graph of this electric field, sometimes in the question will be asked to draw the graph of the electric field, sometimes will be asked to draw the graph of the potential field or potential lines, okay. So before drawing those graphs, we'll first revise what are the rules of electric field or field lines and what are the rules of potential field lines. Okay. Now we have rules on electric field lines on the left and rules of potential lines on the right. Okay. So before learning about field lines and potential lines, okay, the first thing that you have to understand is the relation between electric field lines and electric potential lines. Okay. See, field lines and potential lines always intersect each other at 90 degree. Okay. So field lines and potential lines always intersect each other at 90 degree. What do I mean by that? See, we already know that electric field lines, due to a infinite charge carrying sheet, would look like parallel planes, isn't it? This is electric field lines. So how would the potential lines of this electric field look like? The potential lines would look like somewhat like this. This is one potential line. This is another potential line. This is another potential line. This is another potential line. Similarly, if you have a point charge, how does the electric field look like? If it is positive charge, the electric field goes outside. If it is negative charge, the electric field would go inside, isn't it? Out here, the potential lines look somewhat like this. Okay, this second potential line, the inner circle was the first potential line. The third potential line would be a even bigger circle and so on. Okay, what I'm trying to say is at point of intersection, okay, whenever electric field lines and potential lines intersect each other, they'll always intersect each other at 90-degree angle. See, they intersect each other at 90-degree angle. Whenever they're intersecting, they're always intersecting at 90-degree angle. Whenever they're intersecting, they're always intersecting at 90-degree angle. Okay, so field lines and potential lines always intersect each other at 90 degree. The second point that I'm going to tell is positive charge. Okay, always flows from higher potential to lower potential. That means if there is a positive charge, I kept a positive charge out here, okay, with zero initial velocity, no external force. How would the positive charge move? In the direction of electric field or in the direction of electric field lines, okay? So the positive charge would move from here to here, no? And this was one of the potential. Suppose this was one of the potential lines 1. This was one of the potential lines 2. Okay. So a positive charge would flow from out here to out here. That means this potential lines has a greater value of this potential line. That means potential lines 1 has greater value than potential lines 2. Or positive charge always flows from higher potential to lower potential. Similarly, if I kept a positive charge out here, okay, this electric field was generated due to this charge, that's fair and fine. I kept another positive charge somewhere around here, okay, with zero initial velocity, no external force. How would the positive charge move? Along the direction of electric field lines, okay, so it would move from here to here. So let's say this as potential lines 1, potential line 2. What I'm trying to say is potential line 1 always has greater value than potential line 2. That means positive charges always flows from higher potential to lower potential. Okay. And negative charge, just the opposite. Negative charge flows from lower potential to higher potential. Okay. See, for electric field lines, we can write out the line that positive charge always flows along the direction of electric field lines. Okay. What I'm trying to say out here is, suppose I kept a positive charge out here with zero initial velocity, no external force. What will happen? The positive charge will flow along the direction of the electric field line. Similarly, if I keep a positive charge out here, it will flow along the direction of electric field lines. Okay. See, what I'm repeating again and again is zero initial velocity, no external force. That means what? Under no external influence. Okay, naturally. Similarly, negative charge would move opposite to the direction of electric field lines. Suppose I keep a negative charge out here, okay, it will flow along this direction. If I keep a negative charge out here, it will flow along this direction or opposite to the electric field lines, isn't it? Now one more thing. See, you can always understand this by analogy. Okay, suppose for gravitation, the positive charge is always equals to positive mass. Just for analogy, just for comparison, okay, positive charge is compared with positive mass, okay, and there is no concept of negative mass, but it will behave. Suppose negative mass existed, it will behave in a matter of negative charge, okay. So suppose this is earth, this is ground. How does acceleration due to gravity look like? Downward g. So gravitational field lines would look somewhat like this, isn't it? Gravitational field lines would look somewhat like this, okay, and potential lines would look somewhat like this. Okay, understood? The red is potential lines, the black is gravitational field lines. Now if you keep a mass out here, okay, 5 kg mass out here with zero initial velocity, no external force, it would move from higher potential lines to a lower potential line. That means it would move from this potential line to this potential line. So a positive charge or positive particle always moves from higher potential to lower potential, and positive particle always moves along the direction of field lines. So this positive mass would move along the direction of gravitational field lines, isn't it? Understood? Condition is there is no initial velocity, there is no external force. Okay. Now the third rule is field lines will never intersect each other. Field lines will never intersect each other. Potential lines also never intersect each other. But field lines and potential lines can intersect each other. Okay. One field line will never intersect with another field lines. One potential line will never intersect with another potential lines. But one electric field lines and one potential field lines can always intersect each other. And they should intersect each other. Understood? And one more doubt I have. Okay. What about negative potential line? I always said no. A positive charge would always move from higher potential to lower potential. So suppose I have two potential, okay, and potential in electrostatics is given by volt. The unit of potential in electrostatics is given as volt, okay. So suppose I say phi 1 is equals to, or there are 2 volts, okay. Phi 1 is equals to minus 2 volt, phi 2 is equals to minus 5 volt. Which one of them is higher, minus 2 volt or minus 5 volt? Obviously minus 2 volt is bigger than minus 5, no? Minus 2 is closer to 0, minus 5 is farther away from 0. Understood? So minus 2 is greater than minus 5. So if a charged particle is there, if two potential lines are there, okay, minus 5 volt and minus 2 volt, the positive charge would always flow from minus 5 volt to minus 2 volt. Okay. Similarly, if another two charges are given, 5 volt and 3 volt, okay, 3 volt, 5 volt, and 3 volt. Where would the positive charge move from? The positive charge would move from 3 volt to 5 volt. In positive numbers, which one is greater? The one with greater magnitude is greater. Understood? So remember this. When I'm talking about higher potential to lower potential, I'm also considering the sign of the potential. Okay? That means minus 5 is always lesser than minus 2, whereas plus 5 is greater than plus 2. Understood? Okay, let me summarize what I have said out here. Okay? A field line and a potential line would always intersect each other, and the angle of intersection is nothing but 90 degree. Okay, positive charge under zero initial velocity, no external force, would always move from higher potential to lower potential. Okay, and the third one is two field lines would never intersect each other, two potential lines would never intersect each other. Okay, so one more thing. Okay, electric field lines can never form a closed loop, whereas potential lines can form a closed loop. Okay. Now using these rules, we'll try to figure out the graph of the field lines in the previous question. Okay. See, using the rules, okay, we have to find out the field lines and potential lines. Fair and fine. Now first I'll solve part B of the question. Okay, we'll understand little bit later why. So this is y-axis, this is x-axis. So first I'll draw the potential line. V is equals to AXY. Have you seen this type of graph? So have you seen this type of graph? This type of graph is nothing but hyperbolic graph. Hyperbola means y is inversely proportional to x, okay, or y is directly proportional to 1 by x. How does those graph look like? Those graphs are nothing but hyperbolic graph at a very low value of constant. That means at suppose potential is equals to 1 or positive 1. The graph would form this line and this line for negative values of x in this quadrant, for positive values of x this quadrant. Okay, at potential is equals to 2, this line and this line. Potential is equals to 3, this line and this line. Potential is equals to 4, this line and this line. Okay, so I can say that these are higher values of potential, sorry, these are lower values of potential, and as I go farther away, these are higher values of potential. Similarly, if V is negative, okay, suppose potential is negative, so at very low value of magnitude of V, would form this line and this line. As I increase the magnitude of V, that means minus 5, okay, minus 5 potential, minus 10 potential, okay, the graph would look somewhat like this. Okay, and I do know that positive charge always flows from higher potential to lower potential, isn't it? So electric field lines will go from higher potential to lower potential, and electric field lines are always perpendicular to the potential lines. So out here, the field lines would always look somewhat like this. Okay, field lines would always look somewhat like this. Always goes from higher potential to lower potential, higher potential to lower potential, isn't it? See, we know that negative of minus 10 is lesser than negative of minus 5. So in the negative quadrant, that means in these two quadrants, more higher is the magnitude, lesser is the potential. So we get a graph of electric field lines, which are these arrows, and potential lines, which are the red dotted lines. Fair and fine. Now we'll do part A of the graph. X or Y axis, and this is nothing but X axis. Okay. If I see this graph is also hyperbolic in nature. Okay. But this graph, the equation would look, see, for positive 1 volt. Okay. For example, I'm determining the value of A to be 2 or 3 or something like this. For positive 1 volt, the graph would look somewhat like this. 2 volt, the graph would look somewhat like this. 3 volt, this line and this line. Okay. Now, as I decrease the potential to negative quadrant, that means minus 1 volt. Minus 1 volt would look somewhat like this. Minus 2 volt would look somewhat like this. Minus 3 volt would be more lower and more upper like this. Okay. So from these lines, I'll always say that, okay, potential lines always flows from higher potential to lower potential. Okay. So the graph or electric field lines would go somewhat like this. Electric field lines would go somewhat like this in the downward quadrant. Okay, higher potential to lower potential or higher potential to lower potential. The graph would look somewhat like this. Okay, now one more confusion you might have. So how do I know the graph would look or the potential line graph would look like this? There are few standard equations that you have to remember. Equation of straight line, or how does the graph look in a straight line? Trigonometric functions, then exponential functions, logarithmic functions, equation of parabola. Equation of parabola and quadratic are more or less same. Equation of ellipse, hyperbola. Okay, so these are the few fundamental equations that you have to learn. This will be taught in mathematics in the subject of mathematics. Otherwise, com complex equations or complex graphs won't be important from a JEE perspective. Okay, I made a little bit of mistake out here. Okay, it goes from higher potential to lower potential. So the direction of arrow should be this one. Okay, not this one. This should be the direction of arrow. That means this was 1 volt. Okay, this was 1 volt and this was 1 volt. Okay, then 2 volt line, 2 volt line, 3 volt, 3 volt, 4 volt, and so on. Out here, minus 1 volt, minus 1 volt, minus 2 volt, minus 2 volt, minus 3 volt, minus 3 volt, isn't it? And potential always flows from higher potential to lower potential. Okay, so the direction of arrow should be reversed. Okay, part A I have did it correctly. Understood? Okay, so that's it. Similarly, in this question, potential is given by this equation. We have to find out the electric field. Electric field is nothing but EXI plus EYJ plus EZK. Okay, EX is nothing but minus DV AX square plus AY square plus PZ square by dx. Anything apart from x is treated as constant, minus 2ax. Similarly, EY would be minus, I'm just writing EY and EZ. In this equation, anything apart from y is treated as constant. In this equation, anything apart from z is treated as constant. So electric field would be minus 2axi minus 2ayj minus 2bz. Okay, okay. And if I plot this equation or if I plot this graph would look somewhat like conic sections. Okay, how do I know? This comes by practice. Okay, the graph of complex equations are not exactly required, or you're not required to know from the perspective of physics. However, basic graphs, it's very advantageous to know the basic fundamental graphs. Understood? As I decrease the value of as I increase the value of a and b, this graph would look more and more like two separate conic section. And as these values are, as the value of b is decreased, this would be more like a cylinder. Okay. What's important out here is the equation from potential lines to field lines. Or if the equation of potential lines are given, how do I derive the equation of electric field lines? Or if the electric field lines are given, how do I derive the equation of potential lines? These are these two things are the fundamental things that is important in this question from a JEE perspective. Understood? Okay. This question will give you the clarity between electric field and potential. Okay. In this question, there is the insulating sphere, and charges are distributed uniformly inside the sphere, inside the volume of the sphere. We have to find out the potential at any point in space, irrespective of it is inside the sphere or outside the sphere. Okay. So suppose this is the center of the sphere. Suppose I'm taking the potential at any point in space. That means I can find out the potential at R out here, or value of potential out here. Okay. So how I'll try to approach this question is I'll draw a graph. The y-axis will represent the value of potential. Okay, the magnitude and the sign of potential. The x-axis will represent the distance from the center of the sphere. The x-axis will represent the distance from the center of the sphere. Okay, see, at x is equals to 0, it is at the center of the sphere. So let's name this variable r. Let's name this variable r. Okay, at radius of the sphere, that means value of capital R, what will be the potential? Okay, so if this is the radius of the sphere, or capital R is the radius of the sphere, okay, whenever we have electric field outside a sphere, what was told in class? Okay, we'll always have to consider the sphere as a point object, isn't it? So this entire sphere would be considered as a point object situated at the center, and the formula for electric field outside the sphere is given as k q by r square, where r is the distance from the center of the sphere, isn't it? Now see, potential is nothing but minus dv is equals to e dot dr. Okay, or if I integrate both the functions, minus v, or see, I can either do indefinite integral or definite integral. Okay, if I do definite integral, I have to put up the limits. If I do indefinite integral, then I have to put out a constant and give the value of boundary condition. Both values will be same. Since I'll be doing definite integral, okay, the lower value of potential is 0. That means I'm calculating the potential to be 0. Okay, or I'll do one more thing. I'll try to put the limits later. Okay, let's just solve the function level. Or minus v is equals to e dot dr. What is the, if I differentiate this, or sorry, if I integrate this, what would be the equation? Kq by r to the power minus 2, okay, plus 1 divided by minus 2 plus 1, isn't it? And this is the equation. Now let me just simplify the equation. Minus v kq by r to the power minus 1 divided by minus 2 plus 1 minus 1. This minus and this minus would get cancelled. So v is equals to kq by r to the power minus 1. Okay, I have to put out the limits out here. Or v is equals to kq by 1 by r to the power minus 1 can be written as 1 by r. Kq is constant, no? Okay. Now see carefully. The upper limits and lower limits of potential. Okay, in the chapter of gravitation, there was something called potential energy difference, no? But the ground was taken as zero potential energy or datum line or reference line. The potential energy at reference line is always zero, isn't it? And then you find out the potential at any other point. Potential at this point is equal to mgh from the reference line. Okay, similar type of concept will apply out here. But in this concept, where is the reference line? If you see properly, okay, 1 by r is equals to 0 at infinity. At the value of r is equals to infinity, the value of potential would be 0. That means potential energy at infinity is equals to 0. So that means infinity is treated as datum line or baseline. Okay, so potential energy at infinity is treated as 0. Understood? R is treated as infinity. Now as I bring the value of, or as I bring the positive 1 coulomb from infinity to any other point, okay, the value of potential will differ by this formula kq by r at this point in space. Okay, so out here I'll give v minus 0, which is equals to v is equals to kq by 1 by r minus 1 by infinity, which is equals to kq by r. Understood? If I just skip a shortcut, 1 by r minus 1 by infinity, 1 by infinity becomes 0. Okay, so it is nothing but 1 by r, and 1 by r I can write it as 1 by r. This much is understood. So potential at any point outside the sphere is given by the equation kq by r. Okay, and this equation is nothing but rectangular hyperbola. So the graph would look somewhat like this. As I go towards infinity, the value of thing will be, or the value of potential is equals to 0. Okay, let me draw the graph somewhat like this, rectangular hyperbola. And this graph is only valid for points outside the sphere. Understood? So part B of the question is solved. Or part, not part A, this is another part of the question. Now as I go inside the sphere, okay, the formula is K, or electric field. Electric field is equals to K Q inside by R square, isn't it? See, outside the sphere, Q inside is nothing but the total charge. Okay, any point outside the sphere. Okay, if I apply KQ inside, inside is nothing but this much charge only, no? Out here also this much charge, out here also this much charge. So KQ inside by R square. Out here also if you write KQ inside, it doesn't make a difference. Okay. However, when you're traveling inside the sphere, as soon as you're going inside the sphere, Q inside would be a little bit different. What I'm trying to say is, suppose I'm trying to find out the electric field out here. Okay, the electric field out here would be nothing but this distance r. Okay, and what is q inside? Q inside is nothing but charges inside this sphere. Okay, now see, if I say the charge distribution is uniform, that means what? The charge density is uniform, or charge density is constant. So if charge density is constant, charge density is nothing but charge divided by volume, or total charge divided by total volume of sphere, which should be equals to charge inside the volume that I have taken, charge inside the volume that I have taken, divided by volume inside this sphere, or volume of this much, which is equals to 4 by 3 pi r cube, isn't it? Now if I just take these two equation, okay, q by r cube would be nothing but q inside by small r cube, by small r is the distance from the center, and if I simplify it, q inside is equals to small r cube divided by capital R cube into total charge. Small r cube is nothing but the distance from the center. Capital R is nothing but the radius of the sphere. And if I substitute this formula q inside out here, it is nothing but electric field is equals to k r cube by capital R cube into q total divided by r square. Okay, r square, isn't it? These are and these are would get cancelled, so we'd get the value of electric field as E as k q r divided by r cube. So as I go inside, okay, my formula changes to, or the formula for electric field changes to this value, isn't it? K cube by r cube is constant. This r is nothing but the radius of the sphere. Even if you go inside, okay, the radius of the sphere will always remain constant, no? This r would change as I go inside. Understood? So k q r by r cube. Now to find out potential, potential is nothing but minus dv is equals to E dot dr. That means if I integrate it, okay, or minus v is equals to, I have to integrate this function k q r divided by r cube into dr. This entire term is constant. K cube by capital R cube is constant. So it is the integration of r dr. R dr. Integration of r dr is nothing but r square by 2. R square by 2. Okay, fair and fine. Okay. Now listen to me carefully. Okay. I have to put the limits of this integration. This integration. Okay. Now what is my reference point? I have to find out a reference point, no? See, I cannot use reference point using this formula, okay, at infinity, because this formula is not valid for infinity, no? Okay, so my reference point would be at the surface, okay, irrespective of the formula I use, irrespective of this formula or this formula, okay, the potential of the surface would always have a same value, no? Understood? The potential of the surface would be same irrespective of the formula I use, either this formula or this formula. Okay. So if I go inside, what is the potential at surface? Potential at surface is nothing but kq by capital R. Okay. Potential at surface is nothing but kq by capital R. So potential at surface kq by capital R. What is the potential at this point? I have to find out. So this is nothing but variable v. Radius at surface is nothing but r. Okay, and radius at point r is equals to r. Understood the limits? Okay, now when you have understood the limits, the thing becomes much more easy. Or minus v minus kq by r, kq by capital R is equals to kq by r cube into r square by 2 minus capital R square by 2. Understood this much? Okay, now what I'll do is I'll just solve this equation out here, okay, in this space. So if I multiply this minus in this equation, it will be capital R square. That means these two variables will get inverted, or v minus kq by r is equals to kq by r cube into r square by 2 minus small r square by 2, isn't it? Or potential inside the sphere is kq by r cube into r square by 2 minus capital small r square by 2. Okay, not capital, small. And I have to take this kq by r to the right hand side. So plus kq by capital R. This much is understood. Okay. Now I can multiply in this parameter or in this variable. I can multiply the numerator by r square and denominator by r square. Okay, into r square divided by r square, isn't it? So denominator would become r square into r is nothing but r cube. Understood this much? Now I can take kq by r cube constant from these two terms. So potential at this point is nothing but kq by r cube into r square by 2 minus small r square by 2 plus capital R square. Okay, now it is getting cluttery out here also. I'll just solve it out here. Okay, I'm just hunting for empty spaces. So V is equals to K cube by R cube. Okay, K cube by R cube. R square by 2 plus R is nothing but 3R square by 2. 3R square by 2 minus small r square by 2 minus small r square by 2. Now if you notice out here, the potential at R is equals to 0, or the potential at the center of the sphere is nothing but K Q 3R square by 2. Okay, so this equation or this graph, okay, would look somewhat like this. Okay, as I go from surface to the center, the potential would keep on increasing. Okay, and what is potential? It is nothing but negative of work done by electrostatic force. Where is the datum line? At infinity. Where is the baseline? At infinity. So if you bring a positive charge from infinity to at the center, okay, the work done by electrostatic force is negative, so the potential would be, or potential energy would be positive, and the potential energy at center is nothing but given by this value. Understood? Okay, potential energy of positive 1 coulomb is nothing but known as potential. Okay, force on positive 1 coulomb is nothing known as electric field. Okay, so at the center of the sphere, potential is equals to k cube by r cube. Put r is equals to 0, so 3r square by 2 into k cube by r cube. R square and r cube would get cancelled, so it would be 3 by 2 k cube by r. Okay, inside the sphere as a function of distance r from the center would have this equation or this graph. Understood? And this kind of, or this graph is also important for the chapter of gravitation. Okay, I have to find out the potential at the center of the earth, or from the surface of the earth to the center of the earth. But in the chapter of gravitation, what happens is infinity is datum line. Okay, reference line is infinity. Potential energy at infinity is 0. Okay, but gravity forces are attractive in nature, no? So displacement is in the direction of gravitational force, isn't it? Okay, so work done by gravitational force would be positive. If work done by gravitational force is positive, potential energy or changing potential energy is negative. Understood? Potential energy or changing potential energy from reference line is nothing but work done against a conservative force, so potential energy would be negative. Okay, the magnitude of everything in the chapter of gravitation would be same, except this graph would be mirrored along the x-axis. That means the graph would look somewhat like this. Okay, understood?